Pluto, a far-off and clandestine planet, was once thought to be a part of our nearby planetary framework. However, later, astounding statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have pushed Pluto back into the spotlight. They suggested that this icy world might be on a potential impact course with Neptune. How could this be possible, and what consequences would such a devastating event have? Could this be a fascinating cosmic anomaly, or is there more to this impending catastrophe? Join us as we dive into the potential outcomes of a Pluto-Neptune collision. Once classified as a planet and later renamed a dwarf planet, Pluto remains a subject of intrigue in the vast universe. This is evident from recent theories by renowned experts. Pluto's orbit closely interacts with Neptune's, raising concerns among astrophysicists, including Neil deGrasse Tyson and Michio Kaku, who warn of a potentially catastrophic collision between the two, with significant repercussions for Earth. But how could such an event occur? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit. Since its discovery in 1930, Pluto has not even completed a full revolution yet. However, the intrigue doesn't end there. Pluto's orbit is unusually elliptical, deviating significantly from the nearly circular orbits of major planets. A particularly fascinating aspect is its tilt, 17 degrees to the ecliptic plane, making its path noticeably inclined compared to other planets. This inclination and eccentricity add extra layers of complexity to its trajectory. One of the most remarkable aspects of Pluto's orbit is how it crosses Neptune's. For about 20 years during each orbit, Pluto comes closer to the Sun than Neptune, defying expectations based on their positions in the solar system. This raises a natural question. Why hasn't Pluto collided with Neptune? The answer lies in the gravitational interactions of various planets. The study of Pluto's orbit began after its discovery as astronomers sought to understand its peculiar path. Unlike most planets whose orbits lie close to the ecliptic plane, Pluto's orbit stands out due to its steep inclination and eccentric shape. The mystery deepened as scientists realized that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit, despite these complexities, highlights the intricacies of celestial mechanics. The three-body problem in space refers to the challenge of calculating how three objects, like Pluto, Neptune, and the Sun, interact gravitationally. This is similar to predicting the movement of objects based on their initial positions and mutual gravitational influences. In Pluto's case, this problem demonstrates how its orbit, Neptune's, and the Sun's gravity all interact in a complex manner. Astrophysicists use terms like asynchronous libration, orbital precession, and the Kozai oscillation to explain this phenomenon. Asynchronous libration refers to how, whenever Pluto crosses Neptune's orbit, it is at least 90 degrees away from Neptune. This spatial separation is crucial in preventing a collision. Orbital precession describes the slight vertical movement of an orbiting body. For Pluto, this means that when it approaches Neptune or another massive planet, it is positioned above their orbital plane, providing an additional protective measure. The Kozai oscillation explains how the gravitational forces of Pluto, Neptune, and the Sun interact, helping maintain Pluto's orbit and preventing any erratic movements that could lead to a collision. Despite Pluto's seemingly erratic trajectory, this oscillation stabilizes its motion over long periods, revealing that even chaotic-looking systems follow hidden patterns and rules. These factors help keep Pluto's orbit stable, ensuring it neither collides with Neptune nor strays too far from its course. The three-body problem is essential for understanding orbital variations and the interactions between celestial objects. Studying this helps scientists learn more about Pluto, our solar system, and even distant stars and planets. Mathematical simulations in the 1980s revealed that despite these stabilizing effects, Pluto's orbit is still unpredictable. Even small variations in its initial conditions could lead to significant changes over centuries. However, Pluto's orbit has been found to remain stable over immense time scales. Further studies have helped us understand how Neptune, Jupiter, and Saturn influence Pluto's trajectory. There is a unique relationship between Neptune and Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This synchronization helps maintain Pluto's orbital stability. Jupiter's massive gravity also plays a crucial role in stabilizing Pluto's path, preventing it from veering too far into Neptune's domain. Saturn's gravitational force adds another layer of stability. These findings suggest that Jupiter, Saturn, and Neptune work together to ensure Pluto's safe passage through space without encountering significant disruptions. Without these gravitational interactions, the solar system could be a much more chaotic place, where objects like Pluto could crash into other planets or be ejected from their orbits, triggering a cascade of events. Understanding Pluto's orbit is essential, especially in discussions about its potential collision with Neptune in the future. This also gives us a clearer picture of the dynamic nature of our solar system. Pluto's case demonstrates how even seemingly unstable orbits can reach equilibrium through the intricate interplay of gravitational forces and orbital mechanics. Moreover, it highlights the importance of continuous observation and analysis to better understand our place in the universe. The study of celestial bodies often leads us to confront their unusual behavior, and Pluto's orbit is a prime example of this peculiarity. The concept of orbital chaos, which refers to the sensitivity of a celestial body's trajectory to its initial conditions, is clearly exhibited in Pluto's path. Even slight changes in its position or velocity can lead to drastic long-term orbital shifts. Automated simulations have been instrumental in helping researchers understand Pluto's movements in space. These simulations use advanced mathematics to model the gravitational interactions between Pluto, Neptune, and other bodies in the solar system. By tweaking small details in these simulations, scientists can observe how even minute changes can significantly alter Pluto's trajectory. In the late 1980s, these simulations revealed fascinating insights about Pluto's orbit. While stabilizing factors like asynchronous libration and orbital precession help maintain its stability, Pluto's trajectory can still be erratic if its initial conditions vary even slightly. However, despite the apparent chaos, Pluto's orbit remains stable over extremely long time scales, billions of years. This suggests that despite the apparent unpredictability of Pluto's journey around the Sun, there is an underlying order to it. Predicting the movements of celestial bodies, particularly those with irregular orbits like Pluto, is an enormous challenge. The inherent unpredictability of these systems means that long-term predictions are fraught with uncertainties. While mathematical models are invaluable in understanding and forecasting the future movements of celestial bodies, they also highlight the limitations of our predictive capabilities. Could Pluto and Neptune ever collide? Despite the intricate gravitational interactions that have maintained Pluto's stable orbit for billions of years, recent concerns raised by astrophysicists suggest the possibility of long-term orbital changes. While Pluto and Neptune are currently in a stable resonance, external forces such as passing celestial objects, perturbations from other planets, or even hypothetical rogue planets, could disrupt this equilibrium over millions or billions of years. The role of chaos in orbital mechanics. One of the fundamental principles in celestial mechanics is orbital chaos, which describes how small changes in the initial conditions of an orbit can lead to vastly different outcomes over long time scales. Even though Pluto and Neptune's 2:3 resonance prevents a direct collision, simulations suggest that the orbits of celestial bodies in the solar system can evolve unpredictably over millions of years. Some studies propose that the gravitational influence of large planets like Jupiter and Saturn could subtly alter Pluto's trajectory over geological timescales. These variations, although minuscule on a human timescale, could accumulate, eventually destabilizing Pluto's orbit. Could a third body disrupt Pluto's orbit? Another possibility that has intrigued scientists is the potential presence of undiscovered celestial bodies in the outer solar system. Some researchers speculate about the existence of Planet 9, a hypothetical massive planet beyond Neptune, which could be exerting a gravitational influence on trans-Neptunian objects, TNOs, like Pluto. If such a planet exists, its gravitational pull could cause small but significant perturbations in Pluto's orbit, potentially altering its long-term trajectory. Moreover, encounters with passing stars or interstellar objects could introduce additional perturbations. Although the probability of such events is extremely low, the vast timescales involved in planetary dynamics make even rare occurrences possible. The future of Pluto's orbit. Despite these theoretical concerns, current astronomical models suggest that Pluto's orbit will remain stable for at least the next few billion years. The combination of gravitational interactions with Neptune, Jupiter, and Saturn, as well as the protective mechanism of the 2:3 resonance, makes a direct collision highly unlikely. However, the long-term evolution of the solar system remains an area of active research. Future advancements in computational astrophysics, improved observational data, and ongoing deep space surveys may provide a clearer picture of Pluto's fate. What if a Pluto-Neptune collision did happen? If hypothetically Pluto and Neptune were to collide, the event would be catastrophic on a planetary scale. Given Pluto's relatively small size compared to Neptune, it would be completely shattered upon impact. The debris from such a collision could form a temporary ring system around Neptune or be ejected into space, potentially creating new Kuiper belt objects or influencing nearby celestial bodies. The collision could also have far-reaching gravitational consequences across the solar system, potentially altering the orbits of other trans-Neptunian objects and even affecting the stability of Neptune's moons. However, as previously stated, the likelihood of such an event occurring within the current lifetime of the solar system is exceptionally low. Conclusion. Pluto and Neptune's orbits demonstrate the remarkable stability of the solar system, despite its inherent dynamism. While astrophysicists continue to study the potential for orbital disruptions over immense time scales, current models strongly indicate that a Pluto-Neptune collision is extremely unlikely in the foreseeable future. However, the study of orbital resonances, chaotic interactions, and celestial mechanics continues to expand our understanding of planetary motion. As our ability to observe and simulate the universe improves, new insights into the complex gravitational relationships between celestial bodies may further refine our knowledge of Pluto's ultimate fate. For now, Pluto remains a mysterious and resilient world, its orbit a testament to the delicate and intricate ballet of planetary motion in our cosmic neighborhood. From impacting Neil deGrasse Tyson, a driving astrophysicist offers an extraordinary viewpoint on the secrets of our nearby planet group, especially Pluto. Tyson, who assumed a part in Pluto's renaming as a bantam planet, offers important bits of knowledge into the developing comprehension of heavenly mechanics and the general public's renewed interest in disregarded parts of space. Tyson sees the renaming of Pluto as not a downgrade but a fundamental change. In light of the growing information about the diverse objects circling the Sun, he believes that the complexities of orbits like Pluto's reflect how much is still left to explore in space. The ongoing interest in these questions fuels the excitement of space exploration. In spite of Tyson's optimism, his concerns about Pluto's possible collision with Neptune suggest that there are still numerous questions regarding Pluto's orbit. Will Pluto crash into Neptune, or is this simply another case of confusion in the ever-changing universe? Only time and further examination will provide an answer. For now, we are left with an increased interest in how little we actually know about our own solar system. We continue to study these celestial phenomena with the goal of uncovering the secrets that lie beyond. The possibility of a Pluto-Neptune collision raises more questions about the mysterious and intriguing universe in which we exist. The idea of an impact between Pluto and Neptune challenges our conventional understanding of planetary stability, especially considering the current relative steadiness of their orbits. Given Pluto's location on the outer edges of the planetary system, far from the major planets, and Neptune's status as a gas giant with a strong gravitational field, the implications of such an event would be immense for our understanding of gravitational interactions and planetary system evolution. To grasp the dynamics of a potential impact, one must first consider the composition and properties of Pluto and Neptune. Pluto, despite being a dwarf planet, is composed of various substances believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered with nitrogen ice, and its atmosphere consists mainly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas giant, is made primarily of hydrogen, helium, and other lighter elements with a dense, deep atmosphere. A collision between these vastly different bodies would alter their structure and behavior significantly, potentially creating an event visible across great distances. What makes this hypothetical impact especially interesting is the influence of other bodies in the solar system. While Neptune's gravity plays a vital role in stabilizing Pluto's orbit, it is not the only factor at play. Jupiter, with its immense mass and strong gravitational pull, also has a stabilizing effect on Pluto's orbit, preventing it from drifting too close to Neptune. Saturn's gravitational influence further complicates the dynamics of the outer solar system, making a catastrophic event between Pluto and Neptune highly unlikely. However, despite the apparent stability, ongoing research has shown that the relationship between Pluto and Neptune is far more complex than a direct collision course. The gravitational resonance between Pluto and Neptune where, for every 2 orbits, Pluto completes around the Sun, Neptune completes 3, creates a cosmic lock that prevents them from directly colliding. This resonance is a critical factor in ensuring that Pluto and Neptune's orbits, while they cross in the vastness of space, have never resulted in a direct impact. As we continue to explore the relationship between Pluto and Neptune, it is essential to understand the broader context of solar system stability. The forces at play in this delicate cosmic balance extend far beyond the interactions between Pluto and Neptune. For instance, the influence of the Kuiper Belt, a region filled with icy bodies located beyond Neptune, also plays a crucial role in affecting the orbits of distant objects like Pluto. The Kuiper Belt serves as a boundary zone for many dwarf planets, comets, and other small celestial bodies that orbit the Sun. These objects, including Pluto, frequently interact with the gravitational forces of the giant outer planets like Neptune, contributing to the long-term stability of their orbits. Pluto's orbit is not only influenced by the gravitational forces of Neptune, Jupiter, and Saturn, but also by the movement of other objects in the outer solar system. The gravity of distant objects, including the vast number of trans-Neptunian bodies, can occasionally shift Pluto's orbit in subtle ways. However, these shifts are typically so minor that they do not disrupt the overall stability of Pluto's path around the Sun. Interestingly, this complex network of gravitational interactions creates a kind of cosmic feedback loop where the motion of one object influences the motion of others, and small changes in the system can lead to larger consequences over time. While this might sound chaotic in practice, these interactions have contributed to the overall stability of Pluto's orbit over billions of years. Another fascinating aspect of Pluto's orbit is its relationship with the solar wind. As the Sun emits streams of charged particles, these particles interact with the atmospheres of planets and dwarf planets, causing slight yet gradual shifts in their paths. For Pluto, which is so far from the Sun, the solar wind is much weaker than it is closer to Earth. However, these particles still exert some influence on Pluto's atmosphere and its orbit, gradually shaping its long-term behavior. This is another factor that scientists consider when studying Pluto's orbit and its stability over immense time periods. There is also a possibility that Pluto's orbit could change as the Sun itself evolves over the coming billions of years. As the Sun ages, it will eventually enter the red giant phase, expanding significantly and possibly altering the gravitational dynamics of the solar system. This could lead to changes in the orbits of distant bodies like Pluto and Neptune. However, this is still a distant scenario, as the Sun's red giant phase is expected to occur in about 5 billion years. Nevertheless, this future transformation could bring significant changes to the overall structure of the solar system, and the orbits of objects like Pluto may be altered by this process. Beyond the Sun's potential changes, the gravitational influence of nearby stars also has a long-term effect on the orbits of objects in our solar system. Although the closest stars are far enough away that their gravitational pull has little immediate effect, over thousands or even millions of years, a nearby star could alter the orbits of outer solar system objects like Pluto. This phenomenon is known as stellar perturbation, and while it is not something that will affect Pluto's orbit in the short term, it is something that could gradually reshape the structure of the outer solar system over extremely long timescales. Certainly. However, could you clarify whether you want me to continue the discussion in a similar style, or if you have a specific direction in mind? For example, should I explore more about planetary dynamics, space exploration, or Pluto's significance in astronomy?